Welcome, everyone. Today we are taking a deep dive into the underlying mechanics of memory layout in the Zig programming language. To write truly performant and efficient software, we must understand the hidden formulas governing how data is positioned within RAM. On this slide, we see an abstracted isometric view of a memory module. It is important to recognize that not all data types are treated the same way by hardware. While a single byte U8 has an alignment of 1 and can be placed at any address, a 4-byte U32 requires a 4-byte alignment. When we combine these types within a structure, the compiler must often insert padding to ensure every field satisfies its alignment constraints. Take a look at our example struct foo. Even though its 3 fields, 2 single-byte integers and 1 4-byte integer, sum to only 6 bytes of raw data, the resulting memory footprint is actually 12 bytes. This is because padding is added between the first and second fields, and additional padding is added at the end to ensure the entire struct remains aligned when used in an array. As you can see in the array of structs visual, 3 instances of foo result in a total size of 36 bytes. On the right side of the slide, we have outlined the specific mathematical formulas used to calculate these offsets and sizes. These range from standard modulo operations for alignment checks to high-performance bitwise roundup formulas specifically designed for power of 2 alignments. Finally, we must consider the practical implications for data-oriented design. By understanding these rules, we can strategically group fields to minimize padding and maximize cache utilization. Choosing between an array of structs or a struct of arrays is not just a stylistic choice, it is a performance decision rooted in these fundamental memory layout principles. Mastering these details is essential for achieving the level of control and interoperability that Zig provides. In his Data-Oriented Design talk, Zig creator Andrew Kelly reveals a critical skill often missing from formal education: the arithmetic of memory layout. Explicit documentation for these rules is scarce, often existing only as tribal knowledge among low-level systems programmers. The diagram on the right illustrates the organization of a 64-byte node within a larger memory block, breaking down fields such as the ID, position vector, and pointer array. By visualizing the difference between unoptimized and optimized layouts, we can clearly see how alignment gaps and offsets create wasted space. Our goal is to demystify these invisible rules, empowering you to design high-performance types that achieve a minimal memory footprint. To master memory management, we must understand the relationship between size and alignment. First, consider at size of t. This is the total footprint of the type in memory, measured in bytes. This measurement includes not just the data itself, but also any necessary padding the compiler adds to ensure structural integrity. In this illustration, we see a type occupying a total size of 4 bytes. Next, we have at align of t. Alignment represents the strict geometric constraints the compiler must respect. It specifies that any instance of a type must reside at a memory address that is a multiple of its alignment value. For a type with a 4-byte alignment, valid starting addresses are 0, 4, 8, 12, and 16. As depicted by the calipers, when data is correctly positioned on these boundaries, we have a valid address. If the data falls between these multiples, it results in a misalignment error, which can lead to significant performance penalties or system crashes. Balancing these two principles is key to writing efficient, hardware-compatible code. The invariants of memory geometry represent the fundamental rules that govern how data is laid out in memory to ensure hardware efficiency and predictability. Rule 1 states that the size of a type must be at least as large as its alignment. This ensures that every instance of a type has enough physical space to satisfy its own positioning requirements. Rule 2 requires that the alignment of a type must be a power of 2, such as 1, 2, 4, or 8. This is driven by architectural necessity, as binary aligned addresses allow for significantly faster memory access and simpler hardware logic during address calculation. Rule 3 mandates that the size of a type must be a multiple of its alignment. This property creates stride consistency. By ensuring the size is a direct multiple of the alignment, we guarantee that when these types are placed in an array, every subsequent element will automatically land on its required alignment boundary. In the diagram to the right, we see these rules in action. A type with a 4-byte alignment and a 4-byte size occupies a precise block within the memory grid, starting at address 4 and ending at address 8, maintaining the geometric integrity required by the underlying architecture. Let's examine how primitive data types are mapped from their fundamental bit requirements to physical byte allocation in memory. The core logic we follow is defined at the top of the slide. The number of bits required by a primitive is converted to bytes and then rounded up to the nearest power of 2 bytes. To see this in practice, consider a Boolean. While a Boolean logically requires only 1 bit, it is rounded up and allocated a full single byte of memory. Next, we have a U16 integer. This type requires exactly 16 bits, which translates to 2 bytes. Since 2 is already a power of 2, the allocation remains exactly 2 bytes. Finally, let's look at a U17 integer. 17 bits equates to 2.125 bytes. Because this exceeds 2 bytes and our rule requires rounding up to the nearest power of 2, the system allocates 4 bytes of memory for the 17-bit value. This ensures that memory alignment adheres strictly to power of 2 boundaries. When constructing structs in Zig, specifically using extern struct, we follow the rules of the C application binary interface to determine exactly how data is laid out in memory. The first key concept is the alignment formula. The alignment of the entire struct is equal to the maximum alignment requirement of its individual fields. This ensures that the struct can be placed in memory such that all of its members are correctly aligned. To determine the size and field offsets, we use a process called greedy packing. Fields are placed sequentially, but each field must start at the next available address that is a multiple of its own alignment. Looking at the diagram, box A occupies the first unit of memory. If the next field, box B, requires an alignment of 4, it cannot start at address 1. Instead, we must insert 3 units of padding to reach address 4, which is the next valid alignment multiple. Finally, the total size of the struct is not just the end of the last field, it must be the smallest multiple of the overall struct alignment. This ensures that in an array of these structs, every element maintains proper alignment. Using these rules, we can precisely calculate the memory footprint and internal offsets of any C-compatible data structure. To understand the concept of padding, let's analyze this struct containing an 8-bit unsigned integer, A, and a 32-bit unsigned integer, B. While A fits into the first byte at index 0, we encounter a constraint with field B. A U32 typically requires 4-byte alignment, meaning its memory address must be a multiple of 4. To satisfy this requirement, the compiler cannot place B at index 1. Instead, it must skip to index 4. This creates 3 bytes of padding at indices 1, 2, and 3. Consequently, the total size of the struct expands to 8 bytes. With 3 of those 8 bytes being unusable, we end up with 37.5% wasted space. This visualization clearly demonstrates why the order of fields in a data structure can significantly impact memory efficiency. This slide illustrates the significant impact that field ordering has on memory consumption, specifically comparing an ABAB pattern against an ABBA pattern. In the ABAB layout, we alternate between an 8-bit unsigned integer and a 16-bit unsigned integer. Because the 16-bit integers must be aligned to 2-byte boundaries, the system is forced to insert a padding byte after each 8-bit field. This results in a total memory footprint of 8 bytes. By contrast, the ABBA layout reorders these same fields to group similar types together. By placing both 8-bit integers at the start, they occupy indices 0 and 1. This naturally aligns the first 16-bit integer at index 2, satisfying its alignment requirement without the need for padding. Consequently, the second 16-bit integer follows immediately at index 4. This simple optimization reduces the total size to 6 bytes, eliminating unnecessary padding and improving overall memory efficiency. At their core, enums are simply integers. The fundamental rule for determining an enum's memory footprint is that its size and alignment are equal to the integer type required to store its index. Looking at the first example, we have an enumeration with 3 items, A, B, and C. These 3 values easily fit into an unsigned 8-bit integer, or a U8. Consequently, this enum only requires 1 byte of storage. In the second example, we explicitly force the enum to use a U64 type. Even though we still only have 3 items, the memory footprint expands to 8 bytes to accommodate the specified integer size. This demonstrates how explicitly defining the underlying type directly dictates the memory consumption and alignment of your data structures. Let's examine the fundamental differences between arrays and slices, specifically focusing on the concept of the fat pointer. An array, denoted here as MT, represents a fixed block of memory. In this model, the data is stored contiguously, and the total size of the structure is strictly determined by multiplying the number of elements, n, by the size of the individual type, t. Because the size is part of the type definition, it remains constant throughout the life of the array. In contrast, a slice, denoted as shield t, is implemented as a fat pointer. Rather than being the data itself, a slice is a structure containing two pieces of metadata, a pointer to the beginning of a data block and the length of that block. Both fields are of type usize. On a 64-bit architecture, this results in a 16-byte structure with an 8-byte alignment. This abstraction allows the slice to act as a dynamic view into a sequence of elements stored elsewhere in memory, providing significantly more flexibility than a standard fixed-size array. This slide illustrates the structural and functional differences between bare unions and tagged unions. On the left, a bare union, often denoted as an external union, has a memory footprint equal to its largest field. While this is highly efficient in terms of space, it is considered unsafe because the data structure itself does not track which specific field is currently active. The programmer must manually manage state, which can lead to runtime errors if a field is accessed incorrectly. On the right, we see the layout of a tagged union. In this configuration, an explicit tag, usually an enumeration, is stored alongside the data to identify the current variant. This requires a small amount of additional memory for the tag and potential padding to maintain proper memory alignment. Although this results in a larger total size, it provides a safe mechanism for data access, allowing the compiler or runtime to verify the active field before it is used. In this comparison of memory layouts for advanced systems, we examine the differences between the traditional array list, known as an array of structs, or AOS, and the multi-array list, known as a struct of arrays, or SOA. When using a standard array list, each element is stored contiguously. Because data structures often require specific alignment for their internal fields, compilers frequently insert padding to ensure data is correctly aligned in memory. As illustrated here, this leads to internal padding being repeated for every single element in the array. This creates a fragmented memory layout that increases the overall footprint and can hinder cache performance when only specific fields are needed. In contrast, the multi-array list approach reorganizes this data by splitting individual fields into separate parallel arrays. By grouping all instances of data A together and all instances of data B together, we eliminate the need for interfield padding. This results in a tightly packed memory structure that significantly improves data density. This layout is particularly advantageous for high-performance computing and SIMD operations, as it allows the CPU to load only the relevant fields into the cache, maximizing memory bandwidth and overall efficiency. Let's examine a practical example with the monster struct. This structure contains two fields, a pointer to an animation and an enumeration representing its kind. When we look at the memory layout, the pointer occupies the first 8 bytes. Immediately following it, the kind enum takes up a single byte at offset 8. However, due to the alignment requirements of the architecture, the total size of the struct must be a multiple of its largest alignment, in this case, 8. This necessitates 7 bytes of padding at the end, resulting in a total size of 16 bytes. As you can see, this leads to nearly 50% of the allocated space being wasted. To perform a bottle test of our scaling capabilities, let's examine a scenario involving an array list containing 10,000 monster items. The structure begins with a minimal array list overhead of 24 bytes. From there, the memory footprint scales linearly based on the payload size. By multiplying 10,000 items by the 16 bytes required per item, we arrive at a total payload of 160,000 bytes. This mathematical formula has proven highly reliable, accurately predicting the exact memory consumption observed in our benchmark results. To optimize system performance, one must understand the underlying rules of memory layout. Starting with primitives, their size in bytes is calculated by rounding the bit count up to the nearest power of 2. For structs, the alignment is determined by the maximum alignment of its constituent fields, and the total size is the packed size rounded up to the next multiple of that alignment. In the case of enums, the size corresponds to the integer required to hold the index, which can be either default or explicitly specified. Unions occupy a space equal to their largest field, with an additional overhead for the tag size if a tagged union is utilized. Lastly, slices are generally 16 bytes in size, representing the combination of a pointer and a length. Recognizing these internal mechanics allows us to see through the abstraction and optimize our data structures effectively.